kinds of problems that you're going to see in this chapter. So if you have the ability, I would encourage you to have like extra attention here to what's going on. None of the things that we're doing are that complicated, but if you don't understand what it is we're doing and what it is that we're checking or whatnot, it can become kind of overwhelming. Okay? So do the best you can in terms of focusing for today. So what we're going to talk about today are intersections in 3 dimensions. So there's 3 sorts of intersections that we're going to worry about, where we have a line that intersects with another line, a line intersecting with a plane, and then a plane intersecting with a plane. So in 3 dimensions, there's 4 possibilities if you have 2 lines. Okay, so the first one is parallel, non-overlapping. The second is overlapping. The third is intersecting. And the fourth is non-intersecting, non-parallel. Probably the only one that's kind of requires any explanation about what this really looks like, please stop talking, is the non-intersecting, non-parallel. So imagine you have 2 planes that are parallel to one another. So maybe you have a line in each of those planes that looks like this. Those lines will never intersect, but they're also not parallel either, because you can't draw a third plane that contains both of those lines. So that's the 4 things that may happen in that situation. With a line and a plane, you can have, this can be overlapping. That means that the line lies in the plane. You can be parallel, non-overlapping, meaning the line isn't in the plane, but it's still parallel to it. You can be non-parallel, non-overlapping, or non-intersecting, non-parallel. Can that? No, that can't happen. I lied. And then the last one is just intersecting. So what do we mean by intersecting? So here's your plane, and then your line like comes through it like that. Sophie.
Just trying to wrap my head around this. If you have a line that's like this, if you have a line that's like this, but they're like the same, are they still overlapping?
Well, the lines can continue in both directions forever.
Oh, okay.
So yes, those are still overlapping. Correct. Yes. Yep. Cool. All right. And then for planes, you can have overlapping, parallel, and then intersecting. Now, these 2 situations, overlapping and parallel, these are very hard to identify. And they're beyond the scope of this class. But if we look at a situation where we know the planes are intersecting, we can find the intersection. That's within reason that we can do in this class. Keep in mind, what does the intersection of 2 planes look like? That's a line. Yeah. as opposed to these other types where the intersection is just a point. Okay with this idea? So this is just kind of outlining the three situations that we're going to be talking about and the different things that can kind of happen. And what we'll do now is we'll go through and do some examples of these situations and talk about how we check for each of these four possibilities or three possibilities or whatever. Okay? All right. So let's do an example. Hello. Thanks. So with a line and a line, the first thing we want to do is we want to check to see if they're parallel. The way we do that is you're going to take the direction vector from your first line and see if it's a scalar multiple of the direction vector from the second line, or vice versa. Okay? So if the answer to this is yes, if there's a value for k that we can find that satisfies that equation, we know that this is either parallel or overlapping. And if not, it's either non-parallel, non-parallel, non-intersecting, or intersecting. So if it's parallel, then we want to check for intersecting. I'm sorry, overlapping. Excuse me. And the way we do that is I'm going to take the point vector from one of the lines and see if it's on the other line. So let me actually say this is R01 and see if that's on R2. If this is yes, we're overlapping. If this is no, we are just parallel. So if we're not parallel, we check for intersecting, and we do that by just setting the one line equal to the other. And we solve that system and then see if it satisfies the third equation that we wouldn't have used. So this is going to give us an answer for like our S and T parameters. So if we check that against the entire system, if it's yes, if the check works, it's intersecting. And then we can find that point with either the S or T. If that doesn't work, that tells us this is non-parallel, non-intersecting. So that's kind of the gist. That's how we're going to identify these four cases. So first we're going to check to see if it's parallel. If it is parallel, we're going to see if it's overlapping or not by seeing if one of the points from one line is also a point on the other line. If it is a point, then it's overlapping. If it's not, then it can't overlap. If it wasn't parallel at all, we have to check between intersecting and non-parallel, non-intersecting. To do that, we check to see if the two lines are equal to one another. If they are, we can find the intersection using the solution parameters. And if they're not, then we know they're non-parallel, non-intersecting, and we're done. So there's two things that we really need to check every single time. James. With S or T. All right. So let's look at an example here. We'll do a couple. And again, if things get going too fast or you're having trouble keeping up or whatever, keep in mind that we are recording this, and you can always come back and watch this again, because I know that this is not easy necessarily the first time through. While none of these skills are things we haven't done before, we've done all of these skills before. Just keeping track of kind of what you're doing and what it's checking for is sometimes a little bit difficult. So the first thing I'm going to do is check to see if these are parallel. So I'm going to take the slope vector from the first line and see if that's a scalar multiple of the slope vector from the second line. Usually you can just do this by inspection, right? Does it work? Yeah, what is k in this case? -4. Can everybody see that? Because -4 times -1 is 4, -4 times 3 is -12, and -4 times -4 is +16. It has to work for all three components. So we know that this is parallel. So now we need to check for overlapping. So I'm just going to do this by taking the point vector from one of the two lines and seeing if that vector or that point is also on the other line. If it is, and these two lines are parallel, then all the points have to be the same on both lines. If it's not, then none of the points can be the same on the two lines because they're parallel, because they have the same direction. So to do this, we're going to set up a system. Actually, we don't have to do that. We've done this before, right? Just to check to see if a point lies on a line. All we need to do is see if these three equations have the same solution. And each of these cases, they do, right? So they are essentially the same line. These two lines overlap. They have the same direction, and they share a common point, which means they share all the same points if they're going in the same direction. So we call this overlapping. So overlapping lines that are parallel because they have the same direction, right? But there's two different kinds of parallel. There's lines that are overlapping where it's the same line, and there are lines that are actually parallel, going in the same direction and don't intersect, right? Our conventional thinking of parallel. Is that okay? All right. So let's look at a situation where, and obviously if I had parallel non-overlapping, I'd get disagreeing s's here, right? If I solve those three equations, I get different values for s, or if one s value is different even is enough, that'd be enough to say it's parallel non-overlapping. Okay, so let's look at this example then. All right. So same idea here. We're just going to check to see if they're parallel to start. Yeah. Well, they're supposed to work. Did I? So if you look here, I miscopied that. So you're right. With what I wrote down, that wouldn't have worked, but I just copied the problem down wrong from one line to the next. So good eye. Again, if you're, like if I make a mistake and you're not sure what happened, speak up. I'm happy to take a second look. I make mistakes, All right. So we'll start by checking to see if they're parallel. So if I look at the first one, I'd get k is negative 2/3. If I look at the second one, k is negative 5/9. So I know it's not parallel. I could continue and find the third value for k, but it doesn't really matter, right? As soon as I get two values that are different, I know that they can't be parallel. Is everybody okay there? Now we're going to check to see if it's intersecting. So to do that, I'm going to set the one line equal to the other. -1. So this, I can create a system of three equations. Everybody okay there? If I look at this system, how many variables do I have? 2. I have S and T. How many equations do I need to solve a two-variable system? Just 2. So I'm just going to pick 2 of these equations to use. For the sake of this problem, I'm just going to pick the first 2. It doesn't matter which 2 you choose. And while I'm at this, I'm going to reformat them so that I have the S's and T's on one side and the constants on the other, so I can have it set up to put into a matrix. So I have this system. Everybody happy there? I'm going to solve this system now by creating a matrix. You could solve it by hand too if you wanted to. Somebody asked that in the last class, but I like to use the matrix when possible because it's kind of foolproof. So if I type that matrix into my calculator and use the RREF command, I get the matrix 1, 0, negative 2, 0, 1, 2. That first row, if I read the first row, it says 1s plus 0t equals negative 2. So s equals negative 2. If I read the second row, it says 0s plus 1t equals 2. So t is 2. I'm not done yet, though. I have to check now using this. So that worked. That will tell me now they are intersecting. If that check had failed, we'd have non-parallel and non-intersecting. Okay? To find the point of intersection, all I need to do is take either the S or T and plug it back into the appropriate equation at the very beginning. So to do that, real quick here, let's say I use S equals -2. So I'd have R2 equals -2, -4, -1, plus -6, -9, +2, times -2. So that's going to give me then the point. -2 plus 12, that's 10. -4 plus 18, that's 14. And -1 plus -4 is -5. So I would want to include the point of intersection with that as my final answer. Sam? Of course. Yes, this would be something that would be like on a part 2 of the test. Sophie?
So when you use the two equations to find S matrix, you don't need to use the third one because the variable is distributed.
Yeah, because we have only 2 variables, we only need 2 equations. So we save the third equation from our checker. And that'll be the same way on all of these line and line problems and when you're looking to see if they intersect or not. Okay? Okay. So I think that covers all the situations for line and line. Let's look at line and plane now. Well, the nice part is that the steps really remain the same. So the first thing we're going to do is we're going to check to see if they're parallel. The difference here, though, is that I'm going to be checking the direction vector or the slope vector from the line with the direction vectors, plural, from the plane. So if the lines are parallel, then I need to check to see if they're overlapping. The way I do that is I take my point vector from the line and set it equal to the plane. And if we're non-parallel, we have to check to see if they're intersecting. And we do that by taking our line and setting it equal to the plane. So still kind of the same checks, right? The only difference is because we're operating with a plane and a line, these little equations that we're setting up are slightly different, right? But they're the normal, like, analogous argument. Just you're using plane vectors instead of line vectors. So it's really still kind of the same ideas. Let's do an example for this one. So let's say our plane vector is 11, 6, 3 plus 19, 5, 0, A plus 21, 5, -6, B. And our line vector is -10, 1, 9 plus -2, 0, 6, T. Everybody okay with this so far? That's just the problem. So the first thing I'm going to do is check to see if they're parallel. So I'm going to take the slope vector from the line. Yes. What's up? Oh, okay. So that's the slope vector from the line. And I'm going to set that equal to the two direction vectors from the plane. This creates a system of three equations. Yes. So I would do the same thing here. I could pick two equations to make a system and solve that system using a matrix, but I actually see there's an easier route for this problem. Notice equation 3 has only one variable in it. So I can just solve that directly. Hopefully it's easy to see that b has to equal -1. And then using that answer, I can see by plugging -1 in for b, I see that a would have to be +1. And now I would just need to check this using that first equation. And it does work. So what this tells us is that these two guys are parallel. What I need to do now is I need to see if that line is in the plane or not in the plane, right? That's the next thing I'm going to check. So what I want to do is I want to see whether that point that I know from the line is also in the plane. Because if they're parallel and it's in the plane, then the whole line has to be in the plane because they're going in the same direction. So this is basically the same as our overlapping check from before. So I'm going to take the point vector from the line and set that equal to the entire plane vector, or plane equation. Okay with that? This creates a system of three equations. And again, to solve this system, I could pick two equations, turn them into a matrix, use the RREF on the matrix. But if I look here, the same thing is happening as in the previous system. Equation 3 just has one variable in it, so I can solve that for b by hand quite quickly. And if I do the same thing, and I try to solve this for a, I get that a is, what's that, -1, 0, I think, right? That's 1 and then yeah, 0. Thank you. Everybody's okay there? And now I'm going to check that against this equation. So we found that they are overlapping. Basically what this means is that line lies in the plane. Everybody okay with that idea? So we can see that these steps that we're doing, even though the situation is different, it's really kind of the same checks, right? We have to make the appropriate modifications because the equations that we're checking against correspond to lines or planes, but you're still kind of doing the same things, right? The order of the checks are still kind of the same. Are we okay with this one? The last one that we're going to look at is plane and plane. And remember, in this case, you guys are only responsible for intersections. So you're only responsible to be able to find the line of intersection between these two planes. Is all that I need you guys to be able to do. So there's really only one situation here. So there's not like a bunch of checks to do for this problem. So let's just look at the example. Everybody okay there? Okay. So if these two planes are intersecting, how did we check to see if two things were intersecting? We set their equations equal to each other, right? If I wanted to see if two lines intersect, I set the equations for the lines equal to each other. If I want to see if the line and the plane intersect, I take the line equation set equal to the plane equation. Here we're going to set the two plane equations equal to each other. So I'm going to try to get this all in one line. I think if I write these parentheses kind of skinny enough, I can do that. And I'm not going to put a question mark after the intersecting here because we know that these two planes intersect. That's kind of the assumption for this kind of problem. The only situation you're responsible for is when they actually intersect. So this is going to generate a system of three equations. Okay. If I look at this, how many variables do I have? 4. How many equations do I have? That's kind of a problem, right? We need to have the same number, or if we have more equations, that's fine, but having more variables than equations, we're not going to be able to solve this system explicitly and get specific values for A, B, C, and D, but that's okay. We're still going to set this up like a system. We're still going to use a matrix to solve this, but we'll show you how to kind of interpret that answer because we have to be a little bit careful about how we do that. So I'm going to set this up getting the A, B, C, and D's on one side, and then the constants on the other. Note when I'm doing this, I'm being careful because the A, B, C's, D's, and constants all need to line up with each other vertically. So if they're not lining up, you're going to get issues when you try to solve your system. Now that I've written my system, I can translate this into a matrix. And when I solve that system, the matrix that my calculator is going to give me looks like this. We all okay to here? Okay. So if I look, yes. You can just use the fraction command. So if you press the math button, the first option under the math menu is the fraction command. And that works on numbers or matrices or whatever the object is. It'll take the outputs as decimals and turn them into a fraction within reason. Sometimes if the numbers are too big or if the calculator to truncate the decimal, it might not work. So sometimes it just says, nope, not going to do that. But for these problems, it would. So if I look at the first row, let's turn this into an equation, right? So this says 1a plus 0b plus 0c minus d, or I'm sorry, plus d equals negative 1. Right? Where this first column is my A's, my B, C, D, and then like my answer. Everybody's okay there? Now, if I go back and I compare A and D, are these parameters from the same plane? If I go back and I look, A and D are in different planes. Not interested in that then. Let's look at the next line. This says 0a plus 1b minus 1 or plus 0c minus d is equal to 0. Again, different planes, don't care about that. The last row, 0a plus 0b plus 1c plus a half d is equal to negative a half. C and D are parameters on the same plane. That's the equation that I want. Everybody's okay with that? Because of the way the RREF command works, I think you're always going to get that last row is going to be the one that you want. I did a couple of these examples the other day to kind of get ready for this, and that's what happened for me every single time. So we're still all good, right? Okay. So I'm going to use this equation now to pick values for C and D to plug into my equation for my plane. So if I pick C to be 0, what does D have to be? Negative 1, right? Can everybody see that? If I pick D to be 0, what does C have to be then? Yes, negative 1/2. Thank you. Everybody good with that? Okay. This is all I need. I just need 2 pairs of C's and D's. You could keep going and generating more. They don't have to be these specific C's and D's. Any C's and D's that satisfy this equation would be fine. Everybody's good with this? Okay. So now I'm going to take C equals 0 and D equals -1 and plug that into plane 2. So what does this give me? This gives me the point -10, +1, +9. If I do this again with the other point, or with the other pair, I should say, those aren't points. I know, it's a lot. So I do that, and what do we get here? We get -8, we get +1, and we get +3. So what is special about these 2 points that we've just found? These 2 points are on the intersection. By using this C and D equation here, we're able to find points that are actually on the intersection of these 2 planes. So if I have 2 points, we can write the equation for a plane, or for a line, right? So this is our equation for a line. R0 could be either of these 2 points. It doesn't matter. I'm going to use the first one. And then to find my direction vector, I'm just going to look at the difference of these 2 points. So I get that. So my final answer is this. That is my line that is on the intersection of these 2 planes. Of course. Okay. We're going to stop here.